So now that we've introduced power electronics, we've mentioned we're not going to take a closer look at power amplifiers, but let's go ahead and take a closer look at our power supplies. And so I think your author pretty accurately describes our power supplies as the unsung workhorses of the electronics world. And so that is to say that essentially not many people appreciate them in their design process. Maybe they don't consider them as much as they should. And occasionally, as the author details in the book, he has had an experience where he neglected the power supply design, and that caused everything in his circuit to basically not perform as desired. So it's a very important thing to keep in mind when you're designing, even though it's maybe not as fancy and immediately interesting as some of the other circuits that we look at. So what do we mean by power supplies? What's our definition? So in general, we can say a power supply is any system that's delivering electric power. So any system that delivers electric power to a load. Okay, so that would be sort of our more general definition, but we could get more specific for what we're going to look at here. And so again, these definitions, there's some variability depending on where you look, but for the terms of this textbook and for that, because of that, also for this class, what we're going to say is a power supply is a system that's supplying a reasonably constant DC voltage. So a system that provides a reasonably constant voltage DC power to the load or to the rest of the system. So of course here we have a few key words. We're saying it's reasonably constant. We're also looking at the voltage, and we're looking at DC power. And so we're going to dive into each of those in more detail in some later videos. It's worth mentioning that in some rare cases we can have a constant current DC power, but more often than not we'll have a constant DC voltage. And so again, that definition for power supply might vary depending on where you're looking, but for the terms of this class, that's what we're going to define our power supply as. So in order to sort of be able to define some more important characteristics of our power supply, I'm going to draw a simple sort of block diagram. So we're going to have a little box here that's representing our power supply. Let's try that again. Nope, one more try here. There we go. Okay, so this is going to be our power supply. And so on our input side, as we're going to talk about in a later video in some more detail, we're going to have a single phase AC input. So this is going to be our VAC coming in, and we're going to have some AC current coming in. And then our output, like we just defined above, is going to be DC. So we're going to have some DC voltage and some DC current. And so of course I've not shown, but we'll have a load connected on our DC side, and we're connected on our AC side to, for instance, a wall outlet. And so let me just explicitly write here that this AC input is just a single frequency, and we're going to assume for all of our discussions that it is a sine wave. Okay, and like we're going to see here in a second, we're going to be using our RMS phasors, our root mean square phasors, like you've seen in your power systems class, to describe this AC input side. Okay, so before we move on to look at sort of our efficiency of this system, a quick design note. If we're considering this input AC side, we need to be aware that there are different AC voltages and frequencies depending on the place that you're designing for. And so what do I mean by that? Well, I mean in different countries. So I gave the example of using a wall outlet. Well, depending on what country you're in, that wall outlet might be a different value. So here's sort of a table where we have various RMS voltages and frequencies of single phase power available. So we can see here in the US we have 120 volt VRMS at a frequency of 60 hertz. Whereas contrast to that, if we look at Kenya, where a lot of our service projects here at Milligan take place, we see that they have a VRMS of 240 and a frequency of 50 hertz. So it could be a big difference whether you're designing a power supply to work in the US versus in Kenya. Maybe you design a universal power supply that could work anywhere, but that's going to be, of course, more complicated and generally more expensive than if you're designing it to work in one given place. And so some of these other places I've just used as examples because they give a good variety of our RMS voltage. So going back to that idea of a universal power supply, if we want to design a power supply that's going to work everywhere, one other thing that we need to consider is that this value for our from our utility coming at our wall outlet is generally going to vary by as much as 10%. So AC utility voltage varies up to 10%. And so you could see this if you were to take a multimeter and just measure the voltage at various places at various times. Of course, it's not always going to read perfectly 120 RMS. So you're going to see some variation to that. So if we're making a universal power supply, then we need to consider that 10% variation in our design. And so these are just sort of some design tips and pointers, things to keep in mind as you're considering different designs. So universal power supply means we would have to accommodate on our low end. We see of these listed here, which I believe this should be an inclusive list of all the different VRMS values. We see our lowest one is this 100 VRMS that is in Japan. So if we want to accommodate Japan and we say, well, that 100 can also vary by 10%, then we know that that's going to go down to 90% of that 100 VRMS, which equals 90 volts. Now, on the other end of the spectrum, we look at somewhere like Kenya, which has 240 volts RMS. We can say, well, we need to account for Kenya, but that can also vary by 10%. In this case, if we go up 10%, we have 1.1 times our 240 volts, which is going to give us 264 volts. So if we were designing a universal power supply, we'd have to have it work between these two voltages. And then we'd also have to have some way to accommodate for different frequencies, whether we're working at 50 or 60 hertz frequencies. And so for some lab equipment and other industrial equipment, you'll notice there's a switch where you can switch between what type of input voltage it has. Okay, so coming back to our sort of simple power supply here, let's talk about our efficiency equation. So our power in is going to be here on the left side. So let's just write this is going to be our power in our AC, and then the power out is going to be over here on the right side. So from our power systems equation, we have, if we want to talk about the real power in an AC system, so of course that's as opposed to our imaginary or our apparent power, the equation for that was, and so we can say that's going to be our power in, the real power in, is equal to the real part of our voltage phasor, RMS phasor, times the complex conjugate of our current phasor. So the little asterisk indicates complex conjugate, and we divided that by 2. So if we go through that math, what we could show is that is equal to the magnitude of our voltage phasor times the magnitude of our current phasor, and both of those things multiplied by cosine of theta, where this cosine of theta term, so let me indicate that it's just this cosine of theta term, is, you might recall, our power factor. And so of course theta in general is defined as the phase angle of our voltage minus the phase angle of our current. If you're getting flashbacks, don't worry, we're not going to get into that in too much detail. We're just going to mention that briefly as we talk about efficiencies. So that was for our input. So now if we talk about our output, that's going to be a lot simpler because it's just DC. So our output, P out, is just going to be V DC times I DC. P equals VI, so that easy. So now if we remember our basic definition for our efficiency, we had our efficiency is P out over P in. So in this case, our efficiency, which is P out divided by P in, is going to be equal to, so we're just going to have the VDC, IDC in the numerator, divided by our previous equation where we have magnitude of our RMS voltage times the magnitude of our RMS current times the power factor, which was cosine of theta. So that could be, this is a useful equation for designing for the efficiency in our DC power supplies. So one thing to note, another sort of design idea here, is looking at this equation, we could say if we have the no load case, well, if we don't have any load, that means there's no path for the current to flow. We just have an open circuit at our output, so our IDC is going to be 0. And from this equation above for our efficiency, we see if our IDC equals 0, then our efficiency is going to be 0. And so of course I've made the implicit assumption that our power supply is having to consume some power internally. Of course, even if that's a small amount, 0 over a small amount is still going to be 0. So what we're going to want to do is, we're going to see this through some later videos, is we want to design for some optimum output current. So there's going to be some optimum output current that is going to maximize our efficiency, but we're going to have to consider that as we change our load, that this efficiency is going to be changing because our output current might be changing. So we want to maximize our efficiency. Ideally, we would like 100% efficiency, but we know that's not possible. So we still want to consider effects of changing load. So this is, of course, a recurring theme that we're looking at. How does changing load affect our circuit? So that's all for this sort of introductory video on power supplies. So in some later videos, again, we're going to get into some more details of specific configurations.